morning, everybody, depending on where you are. It's my pleasure to introduce today Arnoud Boer, who's an associate professor at the Korteweg de Vries Institute for Mathematics at the University of Amsterdam. His research focuses on various aspects of pricing and assortment optimization problems. And recently, he has started to focus more on societally relevant consequences of price algorithms, such as their potential to reduce waste and their ability to harm consumer welfare by forming cartels. And today he's going to give us a very interesting talk about how long does it take to sell your products. So thank you for accepting being in the seminar, Arnold, and yeah, the floor is yours.
Thanks. Thanks for the introduction and the invitation. And thanks everybody for being here. So today I want to present a very classical topic about a very classical model. Namely the question, how long does it take to sell your product? So what I want to present in this work is basically you have a finite inventory that you sell during a finite time horizon, either with static or dynamic pricing. And then the basic question is what can be said about the sales time. And this is joint work in progress with Tarek Abdallah from Northwestern University. So let's start with the model and then later I will formulate the research questions. So we have a seller who tries to maximize their revenue. They have a finite inventory of Q units and there is a finite selling season denoted by capital T. Customers arrive as a Poisson process with normalized rate 1. So let Tn be the arrival times ordered. When they arrive, they draw a valuation or willingness to pay from a distribution F with survival function F bar. Xn are their valuations. And now they purchase basically if they are within the horizon and if their valuation exceeds the willingness to pay. So at each time the seller sets a price. That can be a non-negative real number, but there's also the shutoff price. That is a typical device. So that's basically the right endpoint of the support of the valuations, because that enables you to shut off the demand in case you are out of stock. So the customer purchase if their arrival time falls within the horizon and if their valuation is at least the posted price upon arrival. Now there's a small subtlety because here's a minus. So it's the limit from the left. That's because, yeah, after the sale, the seller can immediately change the price. So you should look at the left limit here. Now prices should, of course, be measurable with respect to the information that you have, that is the past sales purchase times up to now. And we require that the price is set to the null price if you're out of stock. And so the cumulative sales up to time t, that is the sum of the indicators when the arrival times are most t and the valuations exceed the posted price. If sales is q, then you're out of stock. You shut off the demand. Now, the model is very simple. There is no inventory replenishment, no backlogging, no salvage value, and no marginal cost. But you can, of course, incorporate all these things in the model. And a standard application is airline tickets, but more generally, like perishable products can be framed, can be modeled like this. So, as I said, we consider two modes of pricing, static and dynamic. Static just means that the price is constant over time. It's a very basic policy. And in particular, the optimal static time or the optimal fixed price until you're out of stock. So to define that, let this be the sales given a price P. So then you just sum the arrival times in the horizon where the valuation exceeds P. And then your objective function is to maximize price times the sales. And that's called P star stat as a function of Q and T. So that's your static price. That's what you set as long as you have inventory. And if you're out of stock, you set the null price to shut off demand. Now, the dynamic pricing policy is described in a well-known paper by Gallego and Van Ryzin in 1994. But since I don't know if everybody is familiar with that, I would go over the main ID. So basically, you formulate a dynamic program where the state is the remaining inventory and the remaining time. Now, time is continuous, so we get an Hamilton-Jacobi-Bellman equation, but intuitively you can derive that by discretizing time. So suppose that JKS is the optimal amount of revenue that you can earn if you have K units left and S time left. And so that's not the calendar time, but the remaining time. And then roughly, if you suppose that prices are constant over these small ds intervals, you can write this recursive equation that if I have ds more time, well, what can happen? Either there can be an arrival, which happens with probability 1 times ds plus small ods. The purchase with probability f bar of p, and in that case I earn p plus my future reward, which is then with one uh, fewer inventory, or with 1 minus the probability of the sales, I earn no immediate reward and just the future reward jk of s with boundary conditions. Now, you can bring this term to the left, divide by ds and take the limit. Then you can obtain this equation. There's one subtlety about interchanging the supremum and the limit, but that you can take care of. So this is the equation for the value function, and then the maximizer is the optimal price, P star dynamic, given K inventory left and S time left. So it maximizes this function here. Delta J is the marginal value of inventory. So JKS minus JK minus 1S. How much you earn more when you have 1 unit more of inventory. Now, I also write a max because under some conditions that we state later, the maximizer exists and is unique. And then your posted price. So of course, if you're out of stock, then you set the null price, but otherwise you set the price P star dynamic. So then here you have to give your remaining inventory, Q minus the sales up to time T, and here the remaining time that you have. Yeah, so that's the dynamic policy. Now let's formulate our research question. So basically, yeah, the question is how long does it take to sell K items of inventory when you start with Q units under the optimal static and an optimal dynamic pricing? How does this depend on my valuation distribution? And like structurally, is static pricing, for example, always faster than dynamic pricing, or always slower, or is it indeterminate? Now, these questions have relevance for theoretical research and for practice. Well, from a theoretical side, I think it makes sense to try to understand how these policies utilize the available time. And in fact, I realized that perhaps it's quite a fundamental question because so there is this well-known definition of revenue management, um, namely that revenue management is the art or science of selling the right product to the right customer at the right time and at the right price. Now, this quote is attributed to Robert Cross, but according to another source, it can already be found in some form in the annual report of American Airlines, which I could not access, so I don't know who said this for the first time. But I can imagine, I mean, if you work in revenue management, that you are familiar with a quote like this. Well, if this is the definition of the field, then I think we should answer the question, what actually is the right time to sell this product? And yeah, as far as I know, well, at least for me, I didn't have an answer, but in this talk, you will learn an answer to this question. What is the right time to sell your product? Now, you can also imagine that it has value in practice. There are some reports that practitioners don't comply with the suggestions of their dynamic pricing software, especially if the sales go too fast or too slow compared to what they expect. So it's of course very helpful to have good expectations of how long it actually takes to sell a number of products, especially when you transition from static to dynamic pricing or vice versa. Oh, and you can also use this to develop some visualizations or tools to quickly see which products are really running behind where an intervention is needed. Now, and in this last line of my slide, we'll discuss the literature, which is there. As far as I know, this question has not been addressed in the way that we do that. There are a few other studies that study time-related questions, but the selling time, as far as I know, has not been discussed in the literature. Yeah, so the results that I want to share are not like extremely deep technically, but it's more focused on conceptually to have a feeling of what is the answer to this question, what is the right time to sell your products. So formally, we look at these kind of stopping times. Yeah, so tau stat and tau dynamic. So you can of course define it as the first time that you sales hit k, but then it can be that your tau can be infinity if you don't sell k items. So we basically cap it at t and we say tau is the last time that my tau of kt was the last time that my sales was below k. And if you sell less than k items during the whole horizon, then tau is just capped at t. And the same for tau dynamic, that's under the dynamic policy. So that's the time it takes to sell k units capped at t, or you can also think of it as the time that at least k units are in stock. Now we normalize by the time horizon, and then we're interested in the distributions of these quantities for all values of k, of course, from 1 up to q. Now, in general, there is not an like explicit expression. It depends on the valuation distribution, of course. And in the dynamic case, except a few cases, there's no like explicit solution to the Hamilton-Jacobi-Bellman equations. So therefore, we look at asymptotics to understand these objects. Now, of course, I don't claim that asymptotic regimes, I don't make a statement about, which asymptotic regime is the best, or it's really about uncovering a kind of first order structure to understand how these objects behave. So we look at asymptotics, and then the question is which asymptotic regime, because there are 3 asymptotic regimes at least. So perhaps the most well-known is the fluid regime that was already described in the paper by Gallego and Van Ryzin. So there you let the inventory and the time horizon grow large. And usually one defines that as by considering a sequence of problems indexed by n, and the inventory of problem n is n times some x1, and the time horizon is also scaled by n. Now, in this scaling, all randomness disappears and you get a deterministic problem, and the optimal price is just the fixed price, the optimal dynamic price. So this has been the prevalent regime that has been studied, or the most studied regime in the past 20 years. But recently, 2 other regimes are being studied. So the small market regime, I think the term is first coined by the paper Abdallah and Reed. That means that your inventory gets large and the time horizon is fixed. And the large market regime, that's also studied in this paper, but I think it's first coined by this paper. And they first studied this regime. That's the other way around. Your inventory is fixed and the time horizon goes to infinity. Now, by the way, so in in my model, the arrival rate is fixed, so I scale t, but you can also say t is fixed and I scale lambda. Basically, it's about lambda times t, which you can scale or keep fixed. So there are different ways to define these regimes, but they're all equivalent. Now, the most natural regime to study your question is the large market regime, because we want to say something about how long does it take to sell K units, and then K should be fixed. So in particular, we also consider settings where the inventory is small, even like one. You sell one unit, maybe one asset that's on the market. How long does it take to sell that? Then K is one and Q is one, but also maybe Q is 10 or small numbers. Large numbers also apply, but also small numbers. So then the large market regime where T grows large, inventory is fixed, is the most natural to study. Okay, now it turns out that our results only depend on the tail characteristics of the valuation distribution. And to make that more precise, we define three classes, and they are the three standard classes basically of the Fisher-Tippett theorem of extreme value theory, as where you have the result that the maximum of a random variable under some scaling and some norming converges to a random variable that can be Weibull, Gumbel, or Fréchet, and that defines classes of random variables that correspond to these limits. So in particular, if xu is the right endpoint of the support of our valuation distribution, we assume it has a density to make our life easy, and support is an interval. Then we assume that f lies in one of these three classes. So they all have a condition. So they are short-tailed with an index alpha, light-tailed, or heavy-tailed. Short-tailed means that your support is bounded and that this condition holds. So all these three conditions are the von Mises conditions. That means that there are slightly more general definitions, but this is to make our life a little bit easier. These conditions are easier to work with. So you can like easily verify that uniform distribution satisfies this constraint. If f goes to the right endpoint, then this converges then to 1 for the uniform. Gumbel, again, there are many equivalent definitions satisfied by normal or exponential distributions and the heavy-tailed, for example, Pareto. Then this scaled or generalized asset rate, like fx over the survival function, converges to alpha. We assume alpha is strictly larger than 1. We want to have finite expectations. Okay, so these are the three classes, and we assume that f lies in one of these three. And so short-tailed and heavy-tailed, they also have an index. Now, normally in papers on revenue management, there are typically some other assumptions. Typical assumption is that the profit or instantaneous revenue is, for example, concave as function of the demand rate. But we don't need those types of assumptions. We only need something about the tail. Now, let's start with static pricing, which is a very simple policy, but still it's interesting to study it on its own right, and also to compare it with dynamic pricing. So let's first suppose that the static price is P, so a general, not the optimal one. That lambda T P be the effective demand, so the effective expected number of customers that are willing to purchase in your time horizon, and tau function of P, the corresponding sales time. Well, we just have then a tint Poisson process. So yeah, the K arrival happens after K exponential times, so that has an airline distribution with this. So here, for example, the probability that your normalized sales time of the K item is more than X, and for X 0 to 1, smaller than 1, has this expression, which is just the Poisson CDF, where you have less than K at this time. Now, and this is then the probability that you don't sell K items, you fill in X is 1. That's because we kept the sales time at capital T. Therefore, we get this truncation. Now, let's now consider a sequence of prices, PT for each time horizon T. Then, if you look at these expressions, there are basically three possibilities for the limiting normalized time to sell K items. So the effective demand rate can converge to or can diverge to infinity, or it can go to zero or to a number between zero and infinity. In the first case, the normalized time to sale converges to zero in distribution, but also in expectation. If the effective demand rate converges to zero, then we don't sell anything, so the normalized sales time converges to one in distribution and expectation. And then there is the in-between case. If your effective demand converges to some number as t grows large, then the normalized sales time to sell K items converges to this minimum of Erlang and 1. And there is then an expression for the expectation, that is the 1 over m times the expectation of the minimum of a Poisson with m and k units. So basically, this is straightforward. All we need to do is to understand if I evaluate the effective demand rate at the optimal static price, what happens asymptotically? Now, it turns out that depends on the tail class of the valuation distribution. If my valuations are short-tailed or light-tailed, then the optimal effective demand diverges, goes to infinity. And as a result, my normalized time to sell K items converges to zero distribution and also an expectation. So yeah, that's, I mean, perhaps a bit, well, I don't know if it's unexpected, but what it means is that basically all sales happen at the beginning of the time horizon. All the available inventory has to be sold very, very quickly. It's all front loaded, despite the fact that we have infinite time available. So here we see that static pricing does not really utilize the available time. Everything has to be sold immediately. Now, I don't know if you see this for the first time, you might wonder why should the effective demand diverge when I have finitely many products for sale? I mean, if I have like 10 products, is this really necessary to induce to set the price so low that your demand grows unboundedly? Now, to explain that, it's helpful to formulate your profit as function of the effective demand. And so price, my profit is price times demand. The price corresponding to the effective demand is this expression just by inverting the definition. And the demand is, yeah, well, just if I have Poisson arrivals with lambda rates, I can cap them at my inventory take expectation. So that is my demand. Now, suppose we have bounded support for the valuations. If I then have a bounded sequence of effective demand, then what will happen is that my real demand will always be below Q. And yeah, the lim sup, so not just any finite T, but the lim sup will always be below Q. So to make sure that your demand goes to Q, you need to make sure that it goes to infinity. Otherwise, there's always a small probability or a small amount that you don't get. Now, and in that case, the price is kept at the largest possible price. So then your profit will always be smaller in lim sup than xu of q. Whereas if my effective demand rate goes to infinity, but at small OT, such that my price converges to the largest value, then my demand goes to Q and my profit is higher. So this is an intuition why this should happen. For short-tailed, for light-tailed with infinite support, the argument is different, but the idea is the same. You want to have a lot of demand, and F is such that you can compensate that in the prices in optimal way. Now, interestingly, for heavy tilt, it's different. And actually, we quite enjoyed working on this paper because the static pricing problem seems so basic, but still, we learned a lot about its structure that we didn't know because, yeah, it's not that, because it appears so simple, it's not something that you easily start studying. Namely, that if you have heavy tilt demand, then the optimal effective demand converges to some number. So that means that you have infinitely many time available, but you still want an effective demand of customers who are willing to purchase. That is just a finite number. Depends on Q, it's M star Q. It's the solution to this fixed point equation. M is 1 over alpha times, well, the expected demand kept at Q divided by the probability of seeing less than Q arrivals. Now, and therefore by our earlier results, for normalized time to sell k items under static optimal pricing with heavy tilt valuations converges to a non-degenerate distribution, which utilizes the whole support of the whole time horizon. This minimum of the airline distribution n1 because we cap tau. And this is then the expression for the expectation. Yeah, so there is a difference between heavy tails and short and light tails. Now, why is that? Now, to see where this difference comes from, we have to look again to our profit function as function of the effective demand. So these are the same equations. If we take the first order conditions, because we optimize pi, then we can write that in this way. So d over d prime lambda is lambda times this expression, evaluated in the price. But by definition, the Van Mises conditions tells us that for heavy tilt demand, this converges as z grows large. So, and that implies that the solutions will be bounded. And if you have short tilt or light tilt, then this expression is unbounded. It does not converge if z goes to the right endpoint of the support. So here you really utilize the definition of your heavy tilt class, and that translates into different behavior of time to sell under static pricing. So for heavy tilt valuations, we have a nice non-degenerate distribution and the optimal effective demand converges. The downside is that we have the probability of leftovers. So also in this case, static pricing is not that efficient. You have infinite time available, but nevertheless, it can happen that you don't sell K products. Now, and this is especially problematic if you have not so much inventory. So one case is, of course, if you just sell one unit. If I have heavy tilt demand, say with alpha is 2, so quite extreme, but perhaps, then the probability that you don't sell your product is 28%. And again, my time horizon grows large. So I really don't want to sell it with probability 1 because I'm really targeting a very rare high value customer who may or may not arrive. Now, if I have 8 units, then it's still 9% probability that I don't sell half of them. So as Q is bigger, then this probability for fixed K becomes smaller. But interestingly, static pricing, you cannot sell your last item with probability 1. So even if Q goes large, the probability of at least one unit, not selling one unit, converges to 1 over alpha. Yeah, so that's a fundamental restriction on static pricing. Now, more can be said. And so you say, okay, I have heavy tail demand. I just want M star Q effective demand. That's what I want. Fine. Then we have some asymptotics. So it's roughly Q minus the quantile function of the standard normal in 1 over alpha times square root Q plus other terms. So if you if you have a very heavy tail distribution, that means alpha is between 1 and 2, then this is more than 1/2. So this number is positive. So your m star q is smaller than q. Now this is asymptotically, but it also holds for finite q. So what does that mean? If I have very heavy tail demand, so maybe I have 10 units available, but what I want is to steer the effective demand to, say, 6 units. I'm really setting my demand so low and my price so high uh, because I'm really hoping for this customer that has such a high valuation that your effective demand is below your inventory level. And here there is no limit. The heavier your tail, the lower your effective demand rate. It can even convert to zero. That's just a curious limit setting or boundary result. Okay, that's static pricing. Let's now go to dynamic pricing. And we first look at the time to the first sale, because that turns out to be fundamental ingredient also to study the Kate sale. So dynamic pricing, we have this price. Price is the solution to the dynamic program evaluated in our remaining inventory and remaining time. So what is the time it takes to sell one unit? Well, we just have Poisson arrivals, and the price is non-constant. So the first sale is the first arrival time of a non-homogeneous Poisson process. So we have an explicit expression for that. And the rate is the purchase probability. Yeah? So F bar evaluated in the price at time t. Now, we don't have an explicit expression, but if we have an asymptotic expression for this price, then we are done. Inventory is Q for the first sales because nothing has been sold yet. So if you know this, then we can use that to try to find this distribution. Now, luckily, so Tarek, Abdallah, and George Reed, they have two very powerful, very papers with very powerful results, where they derive these asymptotics in the large market regime. Also in this, I think in the small market regimes, and for all these classes that we considered. So let me show the result. So what they show is that the purchase probability in the large market regime, so a fixed inventory time large, behaves asymptotically as a constant over S, and the price is then like something conform this, so F inverse times 1 minus this rate. Now let's unpack this a little bit. So we have this R star Q, that's a constant. That's defined recursively. So for each parameter kappa, we define a set of numbers. The first one is 0, and then the end one is recursively defined as the root of this equation. That comes a bit out of the sky perhaps, but it's of course in the end all related to the structure of the dynamic program. So k or kappa Vn to the power kappa minus 1 is Vn to the power kappa minus Vn minus 1 to the power kappa, the previous one. So you can recursively solve this. And then you get numbers. They depend on the parameter kappa. And then for short-tailed with index alpha, we take kappa is alpha plus 1 over alpha. For light-tailed, we take kappa is 1. Then the solution is just q. Because if kappa is 1, this is 0, this is 1, and this is just the difference, so you always add 1. And if you have heavy-tailed, then kappa is alpha minus 1 over alpha. Now, what does this mean? So those of you who are familiar with the fluid regime, they know what is the optimal demand rate? Well, that's basically Q over S, the run-out rate. You want to set your price such that you are out of stock exactly at the end of the time horizon. So that's my remaining inventory divided by my remaining time. If you have a lot of inventory, then it's different. Then you want to charge the unconstrained optimal price. But if there is scarcity, then you want to set the run-out rate. Oh, and what is so interesting about this result is that in the large market regime, it's a bit different. For light tilt, we have this intuitive setting. You want to steer the demand to Q over S because then this R star Q is Q. But with short tail demand, you have to set the demand a little higher and you have to set the price a little bit lower. And so these solutions, they have this asymptotics Q plus log Q times a term that depends on K kappa minus 1. And so if kappa is greater than 1, then this number R star Q is a bit higher, so you price lower. And for heavy tilt, it's the other way around. You steer the demand a bit lower and you charge a bit higher. Now, these asymptotics, they are precisely what you can use to derive our first time to sell. So it's not just the asymptotics, but also some other work properties and techniques that we need. But then we are able to prove that the normalized time to sell one item under the optimal dynamic policy converges to a beta distribution with parameters 1 and this constant R star Q that we can compute explicitly. So this is the corresponding distribution function for x between 0 and 1, and this is the expectation of the beta. So interestingly, we have a beta distribution. The parameter only depends on the tail class. So here you really see the influence of the three classes. And the probability of leftovers converges to 0. Also for heavy tail distribution and also, that will come later, also for heavy tail distributions. In contrast to the static price setting. So here are two pictures. So on the left, Q is 1. And you see the density for short tailed, light tailed, and heavy tailed. So here you see that they're quite different. And for example, if you want to sell 1 unit and you have light tailed valuations, then the time is uniformly distributed when that happens. It's more to the left for short tailed and the mass is more to the right for heavy tailed. But if I have, say, Q is 10, then these distributions become much more closer to each other, as you see here. Okay, let's now look at the time of the Kate seal, and there's a very nice idea to derive that. So first we define the remaining time in the horizon. So that's tau bar, K of t. So that's the horizon minus the time of the Kate seal. Now, what you have your horizon, and then you sell the first product, and then you have something remaining. And then you sell another product, and then you have slightly smaller remaining. So with each sale that you make, you cut off a fraction of your available time to sell your product. So the remaining time to after K sales is the product of these fractions. It's the fraction of the remaining times after you sold the first unit. As with J is 1, you get tau bar 1 over tau bar 0. Tau bar 0 is t, that's the first remaining fraction, and then you multiply it with tau bar 2 over tau bar 1, and so on. Now, and then, what is the idea? I mean, you have the first sale, and then you have the remaining time horizon, and then you have again the first sale. But you have, of course, you have less time left, and you have one inventory unit less. Now, of course, these things are all coupled and dependent on each other, but asymptotically, it turns out all these fractions are decoupled. And each fraction of the remaining time that you have converges to a nice independent beta distribution, where the parameter first we had R star Q, and now we have R star Q for the first, R star Q minus 1 for the second, R star Q minus 2, and so on for the next one. So the normalized time to sell K units converges under the optimal dynamic pricing policy to 1 minus the product of beta distributions. And then you can derive also an expression for the expectation. And the probability of leftovers is converges to 0. even for K is Q, you also sell your last item in contrast to static pricing. Now, there is some technical work needed to make this work, but the key idea is this very nice telescoping relation. Now, what is also interesting, because this is perhaps not really informative, but you can do a nice logarithmic time transformation, and it turns out that sales and time are much better aligned to each other if you look at logarithmic time. So if t is the calendar time, then we define ut as minus log of capital T minus small t over capital T. That's the logarithmic time. And then we can define things on logarithmic time scale, like L is the log time of the Kate sale. Delta is the intersales time, the time between two sales on log time. And KT is the sales process on logarithmic time. Now, then what we show is if you look at the vector of intersales times, they converge to a vector of independent exponential distributions. Oh. And my sales process on logarithmic time converges to a pure birth process that starts in zero and has transitions at precisely these rates r star q. So first r star q minus 1 and so on. So yeah, I think that's a very nice way of looking at that in the dynamic policy, you have actually to look at logarithmic times because then the intersales times are just independent exponentials. Now, what is also interesting, we have this expression, where is it? Oh, it's here, with the r star q. But for light tilt, there is a enormous simplification. So for light tilt, this r star m is just m. It's optimal to have the run-out rate and not something higher or lower. Now let tau infinity be the normalized time to sell k units. So it's normalized between 0 and 1. So it has this distribution. Now, normally, if you have like products of betas, you don't get something nice always. But in this case, this is precisely a beta distribution. And not just any beta distribution with parameters k and q minus k plus 1. So that means that your sales times under light tilt valuations are really, really, really balanced. So for example, they are symmetric. The time to sell k out of q units is distributed as 1 minus the time to sell q minus k plus 1 units. The expectation is nicely k over q plus 1. So the sales times, expected sales times are really nicely spaced. Now this is the expression for the variance. And that's perhaps also interesting because the variance, as you can see, is the largest for k is q over 2. Now, so the last products that you sell, their sales time have the smallest variance. Now, and for the last product, that might maybe make sense because in the end, you don't have time. You need to clear this inventory. But the variance is also small for the first couple of products that you sell. And that's perhaps not entirely intuitive because in the beginning, remember you have infinitely many time available. You might think, well, in the beginning, we have so much time, we can, wait for a very rare high value customer, who may or may not come. But we don't do that. There is a kind of discipline in the optimal policy, and there is small variance also for the first product. Only at half inventory, the variance is the largest, and the practitioners will experience the highest level of anxiety if sales are too fast or too slow. So here are a few pictures of the densities for Q is 4, short tilt, light tilt, and heavy tilt, and then different values of K. So you see, for example, if you look at the blue lines, that there is a kind of stochastic ordering. Short tilt is more to the left and heavy tilt is more mass to the right. If you increase Q to 16 or even more to say 64, then all these variances become smaller and they will become more concentrated. And you also see that the differences between the classes is hardly visible anymore. So the sales times depend on the distribution, depend on the tail classes, but their difference is very small, except if Q is small. Now, and there's also the stochastic ordering between the sales times corresponding to the classes. Now, then let's look at the mean and the variance. So for light-tailed demand, the mean is K over Q plus 1. For short-tailed valuation, the mean time of the K-tail is discrete concave. So here are some plots. For Q is 16 and 64. And for heavy-tailed, it's discrete convex. So yeah, for heavy-tailed demand, sales are delayed. For short-tailed demand, sales are accelerated. But interestingly, the highest acceleration point is like not in the middle, but it's a bit at the end. And it's also very nicely, these curves are almost like flipped around the horizontal axis. So the mean, the acceleration or deceleration is the highest at the end. But if you look at the variance, then that behaves much more regular. It's much more symmetric. And the highest variance is roughly in the middle. And the peak of the variance is earlier for heavy-tailed, the blue one, and a bit later for the short-tailed. Okay, so that almost concludes my talk. So let me summarize, and then I also have to answer one remaining research question. But first, a summary of what we have. So for static pricing, we see a kind of dichotomy, short and light-tailed valuations, then all sales are front-loaded, despite the fact that you have all the time in the world. You get a degenerate sales time distribution. Heavy-tailed is better in the sense that we utilize all the time that we have, but then we have leftovers, positive probability. Also, despite the fact that we have all the time in the world. So there's a big contrast between these classes, and we don't see that in the dynamic pricing. And then there is a slight contrast. And so the short-tailed, they have a little bit of front-loading, and the heavy-tailed a little bit of back-loading, but it's like on a completely different scales. There are no leftovers. You can even sell your last unit of inventory. It's a really balanced sales time distribution. So this highlights how poorly static pricing actually handles time. You can, of course, look at this from the lens of revenue maximization. But if you look at it from how they handle time, then this highlights how bad static pricing is. And this can be used to develop some diagnostics. Interestingly, you only need the sales and the time. So to know if you're doing good, you don't need the prices. I don't know if that is useful in some applications, but you can develop diagnostics just based on the sales and the time, and then you can compare them to like confidence intervals of what you expect. And then let me answer my last research question that we didn't address yet. Is static pricing faster than dynamic pricing or not? Now, clearly, for short and light-tailed, the answer is yes, but in general, the answer is no. So you cannot say that because for heavy-tailed valuations, there is no stochastic ordering. So even if you just sell one unit, so here are the distribution functions of the time to sell one unit, 1/1 unit for static and dynamic pricing. And you see that the distribution functions, they cross. Here you have this probability of not selling the unit and the static, and they always cross. So that's interesting that in the heavy-tailed, you just don't know. It's also interesting you see this is the CDF, so static again puts more, is more pulled towards the beginning, and you also see that reflected in the fact that expectation is smaller, or alpha, but no ordering. Now, to conclude, so we started with this definition of the field of revenue management as selling the right product to the right customer at the right time, at the right price. Now, if you should remember one thing about this talk, then it is that we can finally answer the question, what is the right time to sell your product? What is the answer? Well, roughly in the large market regime for light-tailed valuations, the right time to sell product number K has a nice balanced beta distribution. For short-tailed, it's slightly earlier, and for heavy-tailed, it's slightly later. And the difference is small if Q is big, and the difference exists if Q is small, but it's on a completely different scale than static pricing. So that's the answer to this question, and that concludes my talk. Thanks for your time.
Thank you, Arnoud. Very nice talk. Are there any questions from the audience?
So, Arnaud, thank you for a very interesting talk. I enjoyed that a lot. It
Thanks.
seems if you know the valuation distribution, then this is a very complete picture. I wonder, have you thought about, or are you investigating, I don't know what you would call it, but the opposite question where you don't know the valuation distribution and you're trying to come up with a good policy?
I see. So and then you want to just plain learning or also related to this sales time that you somehow want to learn the valuation distribution based on the sales times that you see?
Yeah, that's kind of what I was thinking.
I think that's, I haven't thought about that, but I think that's interesting because but I don't know if you can do that because, so basically the question is, is the sales time profile, does that identify the underlying valuation distribution? Um, I was thinking about it. I think not. I think there can be multiple valuation distributions that generate the same sales time distributions, but I'm not 100% sure. That's more intuition. But then, of course, it's nice to make an explicit counterexample that shows this. So thanks. That's a very nice idea, yeah. And it's related to this diagnostics. Instead of looking at prices or revenues, you just look at sales compared to time and what information that gives.
Yeah, that's what I was thinking. Yeah, but thank you.
Thanks.
Are questions from you? There's a couple of people that unmuted themselves. I don't know if you want to ask something. Okay, if they didn't have a question, I actually had a question. So, thanks for a very interesting talk, by the way. I think it's very important to look at these times. But I was thinking, you have right now your agent is just profit maximizing in the sense that maximizing the sum of all my sales prices, right, over my time horizon.
Yes.
Do you have any intuition what would change if you introduce some discount factor, for example, that I know I care the money at the beginning is more valuable to me, the seller, than at the end?
That's a very good question. I don't know. Yeah, clearly, uh, you don't look then at asymptotics. You just of t going to infinity. Perhaps you look at like the discount factor going to one could be interesting. I mean, the sales will be front loaded if you discount your revenues, but like the structure, I don't know. That's one of the many possible follow-up questions. So thanks. That's a nice suggestion.
Yeah, I don't know how. I think it's very interesting. Things happen to be front loaded because like extreme valuations won't happen with enough probability, but it might depend how extreme are these valuations. Maybe if the valuations are very extreme, then it's still worth to wait for
Yes.
them to get discounted. But I don't know. That's
So the question is whether you still have like a case distinction between short and light and heavy tails, or that discounting
yeah,
just kills it all. And
yeah, yeah. No, maybe there's still a distinction. It's just shifts where the distinction is.
yes, so I think it's an interesting question. I wouldn't know exactly. My intuition would be that usually I don't know. I guess that I can imagine that discounting kills the whole case distinction. That roughly the same structural behavior happens for all classes, but yeah, I'm not sure, of course.
Yeah. I had written down another question at the beginning, but now I don't know if I answer myself at the end. I was thinking, what happens if you have heterogeneous customers, but maybe just whatever distribution you get at the end, then that's the one that matters.
Or heterogeneous in what sense?
In their valuation distributions.
So each customer draws from a different distribution.
Or some finite set of distributions, but
Yeah.
maybe it's just the only thing that matters what the mixture is, and then that's it.
Yeah, it depends. If you don't know, then it's just again a distribution. But if you know customer types, if you observe their type and types have different valuations, then it becomes, of course, interesting if one valuation is heavy-tailed and one valuation is light-tailed, for example. Yeah, in general, I mean, these types of questions, you can, a lot of variants you can study, and you, instead of like the typical profit maximization, you can look at how policies use time. So in general, I would say there are many models where you can study these types of questions that I think are interesting.
Yeah, I think probably airlines do that they know the type and they give you a different price depending on whether you think you're.
Probably.
But yeah, normally it was assumed that you have to put the same price to everybody. Are there any other questions from people? All right. If not, then let's thank Arnoud again. Thank you for the great talk. I really enjoyed it.
Thanks.
Yeah, and this marks an end. Thanks again, everybody, for being here, especially to Arnoud for giving the talk. Yeah. See you next week.
Bye. Thanks for the invitation.